I'd like now to work out a second example of Bohr Sommerfeld quantization. And this example is actually in a different class. We had previously seen for the hydrogen atom an example of a particle moving around in an orbit in 2 or 3 dimensions. Bohr Sommerfeld is also very useful in one-dimensional examples, and those are worked though a little bit differently. So I thought it'd be good for us to try 2 different worked examples, and so this is a one-dimensional example, and this example will be the simple harmonic oscillator. Now, the simple harmonic oscillator is, of course, a critically important system, and it's important in quantum mechanics just like it is in classical mechanics for exactly the same reasons. Namely, that any mechanical system when it's near its equilibrium, the potential always can be expanded in a quadratic form. So near equilibrium, many systems, such as molecules and solids, actually look like harmonic oscillators. And it's important for us to be able to understand their quantum behavior, particularly when we are looking at small systems, such as molecules or the atoms in a solid. So just to recall for you, remember, whenever we do a new quantum problem, the first thing we do is we write down the Hamiltonian. In this case, you have the kinetic energy term, and then the potential energy takes on the simple form 1/2 kx squared, where k is, of course, Hooke's constant from Hooke's law. And if we would like a graph to remind us of that, the potential energy V of x versus x then will just be a simple parabola like, whoops, that was a little crooked, simple parabola like so, right? Where the functional form here is just that the potential V of x is again 1/2 kx squared. So, our main task then will be to try to understand where are the energy levels in the simple harmonic oscillator. Now, one thing to keep in mind is that because my potential has an absolute minimum value at 0 energy, and we also know that the kinetic energy can never be less than 0, the very lowest that this energy ever could be would actually be at 0, and that's why I'm only going to draw the positive portions of my energy axis. But the real question is, how do these energy levels behave? That's what we're going to try to understand. Now, before we go into the formal analysis, a very powerful skill, of course, always is to try to use our physical intuition to guess at the behavior of the spectrum. So let's give that a try. So let's guess at the spectrum behavior. Now, to do that, we can use our correspondence principle and think about what happens to the motion in this system as the energy increases. Now, the basic motion of this system, it's a harmonic oscillator. We understand how it works. More or less, the particle simply is going to oscillate back and forth between a minimum value and a maximum value. And as we increase the energy, this x max value, say, is what we usually call the amplitude. As we increase the energy, the amplitude of the motion will increase. And then the period, now the period is an interesting quantity in the harmonic oscillator. The very famous thing, of course, about the harmonic oscillator is that regardless of the amplitude of the motion, regardless of how much energy you've put into it, the period always stays constant. Now, if the period is constant, that means that the frequency, the classical frequency, stays constant. And in fact, we know the classical frequency nu, right? The famous formula is that it's 1 over 2 pi times the square root of k over m. And that's going to be constant. And if that's constant, then the corresponding radiation frequency we would expect, h nu, which tells us the spacing between the energy levels that we're expecting, that also should remain constant. So what we predict is that regardless of the energy in this system, my energy levels should always show an equal spacing. Now that's a pretty powerful statement. The question is whether or not it actually is true and whether or not our Bohr Sommerfeld condition can reproduce that type of behavior. So let's now carry out the Bohr Sommerfeld analysis for this system.